Hey Miko, welcome back to the podcast.
Okay, it's good to be back.
Excellent. It's been a little while. What's the news on your side?
Plenty of news. I'm not sure where to start. I know we'll cover BetaEarth today. But there've been plenty of things we've been involved with at Asterisk Labs. We are a worker-led cooperative research lab, and we mostly look for interesting applications of open data that tells us something about the Earth. So plenty of things going on. I don't want to go into too much detail given the time constraint, but BetaEarth is one of our sort of like organic uh, contributions where I've just sort of spun a side project for a few days, and it turned out to be interesting enough to share with the community.
Amazing. All right. And BetaEarth, that sounds familiar. AlphaEarth, is it related?
Yes, I think what well at some point there was this opportunity to write a short paper for the ISPRS session on embeddings, and there was like one idea that I had on my mind for a while, which was basically related to the AlphaEarth release from last year. And I think like it was one of the first major embedding product releases that we've seen. Right now, this is getting more popular, but I think it officially, well, maybe semi-officially launched during the Living Planet Symposium in June at the ESA event, and it was quite interesting because while being the first major embedding product release, it was also the first one where we've seen a closed model and an open embedding product, and that was quite
Mm.
interesting to me because it seems like a sort of like obvious thing to do as well in the sense that you can protect your IP of your model. You have full control of who runs the model and where and how. And at the same time, you can provide a global and a huge product to the community for free, essentially.
Mm.
Um, what was quite interesting to me is apart from like being a really capable model, it was interesting to me to think about like how safe this is and how and obviously like whenever we use an AI model in real workflows with Earth observation data, we often want to have this access and get an idea of how the model behaves rather than just the end product. So it immediately was interesting to me to think about how much you can actually retrieve from like how much you can actually emulate the original model's behavior from its embedding outputs alone.
Mhm. Right. Well, that's the motivation. What's the results look like?
Okay, so I guess like I can share the screen and just like give you a quick run through the repo.
Mhm.
And at the same time, I don't know if we want to explain what AlphaEarth does for people who might not be familiar.
Yeah,
But
let's do that.
let me just share the screen. Um,
Because AlphaEarth takes in many inputs, probably more than any other model I've seen.
yes, it's a huge product. It's probably a fairly complex model, unlike BetaEarth. It mostly relies, interestingly, on public free data, essentially from Sentinel-2, Sentinel-1, Landsat, and a bunch of other supporting sensors. And it's quite interesting because um, it uses some of these sensors as targets, or some of the products as targets, some of them as inputs, so mostly Sentinel-2, Sentinel-1, and Landsat, and
Mm.
some of them it uses as both inputs and targets. So it's sort of like a hybrid workflow. And what's also interesting is that it's a fairly complex model that has these really interesting modules that take care of the temporal uh, understanding of these sequences. So in principle, you can create an embedded product that describes any range of time from, I would assume, any subset of the modalities. So you can basically say that you want this descriptor for this sort of time range, and these are the sources that you have available. And in the case of the embedding product that everyone has access to, it's an annual product. So they try to describe a full year of observations with the data that exists there. If I scroll down to the very bottom, there should be, or maybe not the bottom, somewhere here, there should be another, I don't know if you can see. You can go to the original product and access it for free. There is also a mirror on source co-op where you can access this data without Google Earth Engine as well.
Mm.
But in any case, it's we only have access to the annual product, so that obviously limits what we can emulate. We can only emulate the annual product, really, because that's what we have access to. But in principle, AlphaEarth could produce higher granularity, and a lot of users were interested in that. And at the
Mhm.
same time, there's also a discussion about how much sense it makes to go into finer granularity, because very often, like the annual product is supposed to encode all of this information from a full year. So in principle, even if you're interested in a specific month of the year, in a specific dynamic, it should it would ideally be also covered by the annual product. And you have multiple annual products, so in principle, we have access to everything. Um, so I
Mm.
know like the teams at like AlphaEarth and Tessera do work on that quite a lot, on like trying to find these right parameters to produce embedding products that make it practical and also efficient enough to store and distribute. Because it's again, it's a huge product. And like there was an interesting discussion as well in the very early days of embeddings where they were mostly interpreted as tools of compression. And it turns out that like if you have like for many types of embedding products, you actually inflate your data in a way, or at least you create a product that's very, very bulky. And that's the case for AlphaEarth as well.
Okay. So I think AlphaEarth is 64 channels, which would be more than Sentinel-2, right, as a global mosaic, but
Yeah,
possibly better than if you had all these different data sources
exactly.
as
It's like it's supposed to
channels.
compress like multiple sources. So like I haven't seen much work into that, but like it would be interesting to also explore this sort of like compression angle because you are compressing multiple temporal samples. So it's 64 channels, but it's derived from probably like quite a few Sentinel-2 observations, Sentinel-1. And I mean it's up
Yeah,
to the designer how much goes into that.
yeah. And it's not just compression because it should be somehow more meaningful than the combination of the inputs.
Yeah, exactly. So I mean that's another aspect that like depending on the model architecture, unless your model workflow is operating exclusively in pixel domain, where you just process like temporal sequences of pixels and you never actually use any of the neighborhood context. Unless you do that, you actually have a lot of additional information flow that goes into every single pixel, embedding pixel from its neighbors. So like it could be like an additional context that tells you that, hey, this is an agricultural field, but it also happens to be quite close to, I don't know, this type of infrastructure or whatever. So
Yeah.
it's already determined by the architecture that you use. And in case of the BetaEarth, we do use SegFormer, and we also use Dino backbone. So actually, this sort of neighborhood context can be leveraged as well.
Okay, that's a good place to start. So the architecture you mentioned, it's basically a segmentation approach.
And again, like this was mostly an experimental workflow. So if I just find the right place here, there's like 8 models that I've released. With various training strategies, with various architectures. The Dino is an interesting experiment because in principle, like some of the experiments I've done for BetaEarth were mostly exploring how cheap you can make this, like how close you can replicate this without changing much of some pre-training weights. And Dino is an interesting backbone, so we've used that, but it's only with 3 channels, a 3-channel input. So what we can do is actually create these primitives, 3-channel primitives, not only for the RGB, but also for infrared bands and so on and so on. And surprisingly, like you can get fairly high, like fairly comparable cosine similarity with these primitives.
Mm.
Um, Same with land use land cover. And then there's an even simpler version, and that's the SegFormer model, where I only use Sentinel-2 RGB bands, and we still get about 0.83 cosine similarity, and fairly okayish land use land cover. Not amazing, and none of the models are as good as AlphaEarth is. So that's one disclaimer. It's a fairly lightweight model that just allows you to play with these embeddings more, but they are not the
Uh,
same quality as AlphaEarth, but they can be very cheap to run. And again, like an RGB is an amazing example where we just use optical RGB to approximate a lot of the information in the signal, which I think that a lot of people on LinkedIn have already like asked about that. And I think like there's probably like an interesting finding here where a lot of the information in AlphaEarth, like despite this being a temporal descriptor, is actually static. So it does contain a lot of like time agnostic information about a given region that just tells you the overall context, the type of land cover, and so on. So
Yeah.
that's why I would assume that we can get fairly high performance from just like one non-temporal sample and just RGB channels.
Yeah. So do you think LULC is maybe just one example you might want to compare against?
It's not the yeah, it's not a particularly challenging benchmark. And again, this goes back to this being a side project. So like I'd be keen to know like how people like what kind of performance people manage to get with these
Mhm.
encoders. They won't be as I would imagine they won't be as high quality as AlphaEarth, but I think they also can be uh, quite um, quite agnostic. Like they could be still like quite useful embeddings or encodings of the observational data. And the nice thing about it is that like you have full control of like which samples go into your embedding. So when we run the demo, we can actually specify and like the time range, the sensors, and how basically they're weighted down. So like the core model is monotemporal, so you just specify which day of year your samples are from, you pass them through it, and you have some approximation of the annual product. And then you can do it for multiple timestamps and average in any way you like, which also gives you like some interesting. So like most of the experiments I've done weren't really with very specific downstream tasks, but instead they were focused on cosine similarity to test um, different strategies for merging these embeddings from different times of the year and from different sensors. Like for instance, like Sentinel-2 will always give you the highest performance and the best approximation compared to, for instance, Sentinel-1. So sometimes the question is like, does it even make sense to add Sentinel-1 if you only care about cosine similarity? And that will also be task specific. So there's like plenty of experimental work you can do there to kind of see how different modalities and timestamps, depending on location, affect your final embedding and ultimately the performance on your task.
Right. So the objective is to put these models out there and then see how people can evaluate them for different
Yeah,
kind of tasks, maybe with temporal
yeah.
dimension.
So like I have other things going on, obviously, like so this is a side project, so I will probably like test them myself. Like currently I'm mostly interested in and trying to link existing embeddings or like existing latent spaces of the models that we have with representations that are slightly easier to control, such as text, such as multilingual text, and hopefully in the next few months we'll see another release that will actually be I think more interesting than BetaEarth, but BetaEarth is probably like is something I will also test with these specific bridges.
Fantastic. Very exciting. So that's the models.
Mhm. I can maybe show you the demo then, just to so like if you go to the GitHub repo, you will find links to all of the models, and there will be different ways of running the model. So you can use the pip install, run it locally. You can even instantiate your own Streamlit app the same way I did for the demo that you will see in a minute. You can use the existing Colab notebooks. You can load it from like you can. The first one is for a monotemporal example with Major Tom, and the second one allows you to do anything you like over any spatial temporal context.
Hmm.
So you can. There's many ways to get started, but I will just click on the demo. So this is the demo on Hugging Face, and just for the sake of time, I will use the local version of the same demo, just so it runs a little bit faster.
Right. So it's a pretty, I guess, standard sort of map-based interface where you can draw the region you care about and select some other parameters and then hit a button, and in the background, the model is going to generate some embeddings.
Exactly. And I've probably spent more time making this demo, or like same amount of time as I have like writing the actual model. So like both models and the app were like super, super fast to do.
Mhm.
Like and I guess like it's less the app itself is less trivial than the model because I mean Gradio is probably the most common way of producing these Hugging Face demos, but it's doesn't work that good with maps. You can use like a Folium extension for Gradio, but it doesn't work very well with accepting the input. So in this case, we're using a Streamlit version.
Mhm.
And yeah, it works. So I can I don't know. I can maybe select some footprint, and we have pretty much full control here. So we can use uh, an annual product, which obviously takes more time, or we can use a custom date. So let's use one month of July in 2023.
Mhm.
Um, we can save per timestamp embedding. So in case you want to limit the memory usage of your app, you can switch that off if you just want the final embedding. But I'm gonna switch it on just so we can see like how these different components actually contribute to the final descriptor.
Mhm.
And we can also save that per timestamp input. It also saves like a manifest JSON that tells you like which products went into this embedding, which is another nice thing to have when you actually work with these products. And that's one thing that's maybe missing that we'll hopefully see more in the future when you actually know how a specific embedding product was created. So let's
Yeah.
generate it. It first loads a model, it downloads the DEM, and then from Planetary Computer, it will download Sentinel-2 and Sentinel-1 data, I think.
Mhm. So
It's
this
only one
is
month, so it's
fully open
pretty quick.
data.
Yes. And pretty much you can connect it to any source of Sentinel-2 or Sentinel-1 data. These are the two modalities that I just found most universe, like most versatile. And yeah, it's here it is. So right now we see the 2023 average from all products, but we can also observe individual products from a specific date,
Mm.
and also the products that went into them. In this case, we have a lot of cloud coverage from Sentinel-2. So this makes it an interesting example because it's Sentinel. You can see that the Sentinel-1 product is much cleaner. It produces less affected embedding, where you can see how cloud affected the embedding here. And the final output, once you average it out, you actually get something that's quite similar to the original Sentinel-1 product, just because that's the more reliable source of data. You can play with
Interesting.
the Mac cloud cover if you like. Obviously, in Scotland, it can bring variable results, but you can always rely on Sentinel-1. But then, in general, like for many regions, Sentinel-1 will give you a worse approximation of the annual embedding. So there's that. So you generally want, I think, to have a healthy amount of Sentinel-2 data if you want to approximate AlphaEarth.
Interesting. So it's basically got more information, the Sentinel-2, as far as AlphaEarth is concerned.
Mhm. And obviously, like a large portion of the pipeline is also figuring out how to deal with maybe non-standard footprints, how to, most of the models will have a limited receptive field. By the way, you
Yeah.
can download this as zip, so you have access to all information, but I'm going to rerun for this on this weird footprint. But like
Yeah.
a lot of this comes down to like how expensive it is, to do some overlap and to merge embeddings from different sources and different crops.
Question on that, the detail there, because I've seen a few examples of embeddings over large areas where you can see this kind of tiling artifacts, right? How do you handle that with embeddings versus just RGB?
It's a good question. I think this is maybe a slightly under, at least in the space of open source, it's a slightly underexplored aspect. Because effectively what you do is you apply some type of like trapezoidal or linear merging, and you merge. Well, I'm not an expert at creating mosaics, to be fair, so I don't know what's the state of the art when it comes to mixing RGB data. But in terms of embeddings, you often just like average and do some like smoothing between different crops, and I think that's about it. It would be really again, it's an interesting direction for the future, is to like find like better ways and smarter ways to mix data from different crops.
Yeah, because the difference is that one patch has limited context, you move along, that has different context that affects the embeddings.
Yeah, and sometimes it's really tricky. Like the simple mixing, like linear mixtures, are often suboptimal.
Yeah,
But again, it goes back to what you really want to do with the embeddings, because in order for an embedding product to be useful, it doesn't necessarily have to look great. Like we like looking at PCAs because it looks fun, but PCAs are not really useful on their own. Like it only gets useful once you connect it to another model and perform your downstream task, right? So the
yeah,
chances are that the models can still be fine, like can still be fine with these artifacts, right? Especially if you train on artifacts, you might be able to get some immunity against this effect.
definitely. Looks like it's generated something over the water there as well.
Was that, sorry?
Looking at that latest embedding, what am I saying? Some details over the water itself?
Yeah, I mean, I would expect there to be some detail. I don't know how useful these details are, but it will usually produce something like that. Obviously, you get like a lot of speckle in Sentinel-1. Again, an interesting direction would be to look into how like Sentinel-1 behaves and how it affects embeddings. Because again, like what I found is like GEM probably tells you least. Obviously, it just tells you the terrain. So it's just like it gets you to let me see. It gets you to like some interesting like 0.541 cosine similarity. So not trivial either. You can see that like a large
Mm.
amount of information comes from the shape of the terrain itself. But then Sentinel-1 is 0.71, for instance, and then you can get as high as 80s when you add Sentinel-2. And then
Mhm.
finally, when you combine all of them, it's on average is 872. But what's interesting as well is like this dynamic changes, like whether like which modalities are useful to combine depends on where you are and also what exact effect you want to model. So again, like I hope like I'm not sure if, like how performant this model is, but someone can always reuse the same code and train a better model. But what it does allow you is to experiment with these sort of like flow dynamics from different modalities and sampling and so on, because a lot of this could really um, the optimal configuration could really depend on your task and spatial-temporal context of interest.
Absolutely. I think it's really opening the sort of Pandora's box of opportunities for experimentation there. I can see that quite a few masters and PhD students are going to be kept busy, possibly
There,
just
there
from
are quite a few
the
groups doing like
questions raised
really,
here.
really amazing work. There's definitely like some papers that actually measure, try to approximate the information content depending on where you are in the embedding itself.
Mm.
So I think like just like with any like deep like multi-layer model, there's a lot to be discovered once you start really probing things. And like this is, I think, what we need in the community. Like thankfully there we have other models like Tessera, like AlphaEarth that we have more access to, so we can do a lot of that work. BetaEarth is more like an experiment that tells you like how easy it is to maybe reconstruct these models from embeddings alone. And I also think that like potentially like embeddings could be an interesting like additional like regularization in your training regime. So like when you don't have that much data, you can also use this as a model, as a signal that you want to approximate, or you can reuse BetaEarth pre-trained weights as well if you want something that's quite agnostic and also cheap to do. Or maybe you have a different architecture that you want to use, not that is not covered within this GitHub repo. So you just take that architecture, take AlphaEarth embeddings, and you do some pre-training on that, and then maybe you have some specific task in mind that you later want to fine-tune on.
Yeah, and just a really, I guess, niche point, but what's the licensing situation around using embeddings in that way?
So I think it really depends on who releases the embeddings and how. In the case of Google embeddings, it's a Creative Commons license. Um, yeah, and technically you have to use this specific attribution text when you re-release embeddings. In our
Right.
case, we are not re-releasing embeddings; we're releasing a model that approximates these embeddings, but still, I've created the links to the original data set and I've added the
Hmm.
attribution at the very end. But it's another interesting point, and I mean, obviously, like with AI and with models that regenerate some specific data artifacts, there's an interesting discussion um, about how they link to the training data. And obviously, there's a lot of unresolved issues, especially in the computer vision community or like creative arts community in the mainstream AI. That I mean, there's still a lot of like gray area, and there's a lot of obviously like even like violation where you release a model even though the training data didn't really necessarily allow for this type of output. So
Yeah.
like maybe this is I mean it really I'm really not sure like where this leads in the error observation community. I think it will be slightly different and maybe slightly less sensitive. I think it gets very sensitive when you have artists produce artworks and then be completely detached from the product. And in this case, we have an open source solution built on top of another open source solution effectively in case
Yeah.
of the training data.
very interesting topic in itself. Well, thanks so much for the overview and the demo. I just wanted to finish by asking you why you chose the carrot for the logo.
I was just looking for something I could represent with an emoji and something that this easy to remember. And beta is because BetaEarth is because of AlphaEarth, and then the only thing I could really think about is beta carotene for for the emoji association. So I chose a carrot. There was a lot of internal discussions because at some point the carrot had a face, and it was a very controversial topic, an asterisk. And right now we have this faceless carrot that I hope will be good
I don't
enough.
know. I can see a mouth and a couple of eyes and that. Maybe. Wonderful. Well, thanks again. Looking forward to seeing the impact in the community and seeing how people pick this up. And as you said, you have a few ideas how it could be taken forward. So let's see what comes along. I'll put the link to the repository in the show notes. But once again, thanks for joining me and look forward to hearing more in the future.
Perfect. Thank you for having me.
Cheers.
Cheers.